Good evening, everybody. My name is Professor Alistair Lewis. I'm one of the academic staff in the Wolfson Atmospheric Chemistry Laboratories at York, and I'm really pleased to welcome everyone to this online event to discuss the future of clean air and the role of chemistry in supporting this. Firstly, thank you to everybody who stuck with us as we've had to rearrange this event from its original date in the Festival of Ideas in 2024. We were all caught a bit off guard by a surprise election, but it's been great to rearrange it for the start of 2025. We were motivated to have this event to mark 10 years of the Wolfson Labs in York. I'll give a tiny history of this. It was something that was encouraged by one of our previous Pro-Vice Chancellors for Research, Professor Debbie Smith. She really encouraged us to put a facility together that would bring lots of strands of research in atmospheric chemistry into one place. And it was generously funded by the Wolfson Foundation, along with a donation from a philanthropist, Tony Wild. And we opened the first phase of the building in 2014. And within a couple of years, the original 35 occupants had grown to more than 60. And the Natural Environment Research Council then stepped in and then built us an extension on the side, again with more support from Tony Wild. And so today the lab is home to about 80 people, academic and support staff, research staff, PhD and master's students. And it's also home to engineers and computer scientists and policy specialists. And it's this group of people that we bring together that we think means we can do more as a collective than maybe we could as individual research groups. We're also really grateful that we get long-term support from the National Centre for Atmospheric Science. That's part of UKRI. That allows us to do complicated long-term things like building community models, building new generations of instruments and tracking long-term changes in atmospheric composition. So it really relies on not only those people that support the facilities, but those that support the ongoing research as well. And I put a few pictures at the bottom, but actually quite a big proportion of our research doesn't actually take place in York at all. We operate a large observatory in the middle of the Atlantic on Cape Verde. We have instruments that fly on research aircraft and on research ships, and we have instruments at observatories looking at urban air pollution around the UK. And we regularly travel around the world, particularly for air quality research, where we've been in China and India and West Africa, which are some of the places that face some of the biggest challenges at the moment. So tonight's speakers are focusing particularly on air pollution and health, and that's probably our laboratory's biggest topic for research, but it's also home to atmospheric chemists looking at natural biogeochemical processes, the science that's needed to support recovery of stratospheric ozone, for monitoring greenhouse gas emissions, and on emerging science to do with exposure to pollution indoors as well. So there's a lot happening in atmospheric chemistry in a lot of different domains. And one of our challenges for the future is to make sure that we can provide the best physical science evidence to support improving air quality. And for us, that might mean helping improve and redesign laws and regulations. It might mean reducing emissions from individual behaviours or processes or machinery, or possibly remaking some of the chemical products that we use each day. And to get this science used, we're really pleased that we've just entered into a 5-year agreement with DEFRA, which is the department responsible for air quality primarily in government, and that will allow us to work more closely with them, getting the science that we do more quickly into their hands. So just to close, I've been really fortunate that I've managed to work on research projects to improve air quality with all of tonight's speakers, and each one comes at the problem from a different angle, but with a common purpose. But it's still actually rather rare to have medical professionals, atmospheric scientists and engineers in the same room at the same time. So I'm really looking forward to tonight's discussion. So I'm going to hand over to our chair for this evening, Tom Whipple, who is the science editor of The Times. So I'll hand over to Tom, who will make the introduction. So thank you and enjoy this evening.
Thank you Thank you very much indeed, Ali. I'd love to see the sort of competition between the PhD students who get to go to your Cape Verde base in the bottom left and the ones who got to go to your sort of what looked like the picture of the pollution at the end of my road in the bottom right. But look, thank you so much for giving us that overview of the Wolfson Chemistry Lab, and thank you everyone else who's listening in as well. We're going to really need you to ask questions later on. Before we do, though, I'm going to introduce you to our speakers. So our three speakers. Our first speaker is Professor Chris Whitty, who I think genuinely needs no introduction. He's not merely the most famous chief medical officer there's ever been. I think he's probably the only famous chief medical officer Britain has had. But he has done plenty of other things as well. He's worked in Africa, Asia, and the UK, and served as chief scientific advisor for the Department of Health and Social Care and head of the National Institute for Health and Care Research. He is also an honorary professor at the London School of Hygiene and Tropical Medicine and University College London, and continues as a practicing clinician at University College London Hospitals NHS Foundation Trust, and we are honoured to have him here. Our second speaker is going to be Professor Jacqueline Hamilton, who is the Science Director at the National Centre for Atmospheric Science and a Professor in Atmospheric Chemistry at the Wolfson Atmospheric Chemistry Laboratories at the University of York. She develops novel analytic techniques to understand the sources of air pollution outdoors and within homes, and she also studies how these chemicals evolve once they are emitted into the atmosphere. She was awarded the 2009 Destiny Memorial Award for Innovation in Separation Science, and in 2018 was named as the President of the Chemistry Section of the British Science Association. And our last speaker is from industry. Ryan Ballard is Engineering Director for Powertrain at JCB Excavators Limited. He's responsible for all the powertrain engineering activity across the global team at JCB and has a product portfolio of engines, gearboxes, axles, and power generation. He is responsible for leading the design and development of the acclaimed and award-winning JCB powertrains. Ryan and his team are also now central to the decarbonisation strategy for JCB, responsible for product development and introducing hydrogen internal combustion engines. We're going to hear from each of our speakers who, as you can see, they'll each have different perspectives from public health to chemistry to more to the practical engineering side on atmospheric air pollution. What we're going to do is after we've heard them, they're going to introduce each other, and then after they've spoken for 10 minutes or so each, we're going to go for questions. So whilst they're talking, please do use the Q&A function in the panel. Put up those questions. I'll have a look through them and hopefully we'll get through a lot of your thoughts. But let's begin. I'm going to hand over to our first speaker, Professor Chris Whitty.
Thanks, Tom, and thanks, Ali, very much. It's a great pleasure to do this, and I helped a lot by Ali and other members of your group. Did my annual report in 2022 in the middle of COVID on air pollution, and the reason for that is it is an extremely important health problem, and it's also a solvable health problem, and I think that's really key to why I think this is such an important discussion. So I'm going to talk about just 3 blocks of things in the time available. I'm going to just run through what air pollution does in health. I suspect almost everyone on this call knows this, but I think it is sensible just to do that to start off with. A little bit about how we've actually managed to change it to date, and then I really would like to talk about some of the slightly more difficult trade-offs that we need to be aware of. So looking at the health impacts of air pollution, the first thing to say is you don't have much choice about outdoor air pollution. If an industry or a neighbour is producing air pollution near you, you're going to get it. And this is one of the reasons there's a lot of public support for dealing with air pollution, because it's seen to be a problem which is a shared problem across society. And people are correct in thinking that this has a big impact. The current estimates in the UK are that at this point in time, somewhere between 26,000 and 38,000 people a year die largely of air pollution, but it certainly contributes significantly to more than that. Historically, it would have actually been a higher proportion of the population still, and in parts of the world, it still is very significantly higher, but that's still a really substantial number of people are harmed by it. And it affects people through the life course. It can lead to low birth weight babies. In childhood, if children are exposed to air pollution, They can have sudden events like asthma attacks. They can have chronic effects like their lungs develop much less effectively. And these to some extent are logical to almost everybody. But in adulthood, there are also big impacts on long-term health. And many of the largest ones are rather less obvious, I think, in particular cardiovascular disease. So air pollution leads to a very significant increase in heart attacks, strokes in the long term in dementia, as well as slightly more predictable impacts on things like chronic obstructive airways disease, lung disease, pulmonary disease, and lung cancers. And as smoking is going down, fortunately, the proportion of lung cancers, if we don't tackle air pollution that we do to air pollution, will go up, although the absolute number won't. So it's a very important health problem. And now, a problem is not terribly interesting if you can't do anything about it. But in the case of air pollution, we can do a huge amount about it. There is some background level of air pollution that is, in a sense, natural. But the great majority of it people are exposed to is produced by other people. And it tends to come in different groups. And this is where we move to engineering. And engineers have solved a lot of these problems and could easily solve more with the right incentives. A lot of it comes from industry, and we've gone a huge way in reducing, for example, sulfur dioxide, which used to be a very damaging air pollutant because of changes in industry, particularly moving away from coal. A lot of it comes from transport now. Now, transport is important because air pollution can happen in any place, but the place where it's going to do the harm is where people live, work, or play. And transport tends to be where people live, work, or play. So air pollution in places, particularly in cities, is generally substantially more likely to have public health harm than if it was, for example, in the middle of a rural area blowing out over the sea. That has environmental impacts, but in health terms, that's going to be much less of an issue. But it is also important to recognize that there are contributions from agriculture, again, which we could reduce quite significantly with a number of different interventions. Those are all things that cause outdoor air pollution. And as I say, I think there's quite a lot of public support for dealing with this because it's such a shared problem. Then there's a separate group of issues where the science is less clear, and the number of things you can do about it are less obvious, which are to do with indoor air pollution. So if I were to say, look at something like transport, you can say, well, if you reduce tailpipe emissions, for example, electrification, if you change braking, potentially if you change tires, we know that we can tackle this outdoor air pollution. In indoor air pollution, I think the data on what you can actually do to change it is rather less clear. But since most people spend maybe 80% of their lives indoors, indoor air pollution, as outdoor air pollution is going down, it is going down, although it could go down further and faster, indoor air pollution as a proportion, again, is becoming more important. So now just on to some of the trade-offs, and I really just want to mention two, but there are others. The first one is, when is it appropriate for the state to intervene? And it's usually state intervention that's led to companies having to change their practices and therefore asking engineers, please can you design a cleaner engine? Please can you produce a better form of industrial output? And in outdoor spaces, it's a shared space, so the role for government is very clear. In indoor private spaces, I think there's a genuine political question, is that an appropriate thing for the government to be doing? But then there are indoor public spaces, so things like hospitals, supermarkets, libraries, all these kind of environments, they are in a sense philosophically the same as outdoor spaces. So I think the politics of this have to be thought through. Where should the state intervene? And then there are some areas where there are some trade-offs, and I'll just mention two. The first of which is around ventilation. If you increase ventilation, you will decrease indoor air pollution for sure. But by doing so, if you do it just by, for example, opening windows, you can, for example, increase the amount of heat that's lost, particularly in winter, and therefore lead to increases in people's need to use carbon to heat their homes. So there's a trade-off, ventilation versus maintaining the most efficient capturing of heat in space heating. And then there are other trade-offs which are economic, and many of the reasons we've not moved as far as we probably could, in fact, definitely could in air pollution, is because there's sometimes a trade-off between making a change which would reduce air pollution and incurring a cost, very often a capital cost, to improve things. But I'll just finish by re-emphasizing we have come an enormously long way. The great majority of industrial air pollution has been reduced. We've made cars and light vehicles are substantially less polluting than they were 30 years ago because of regulation followed by outstanding engineering.
Thank you very much indeed. So if we now move on to our next speaker, Professor Jacqueline Hamilton.
So I'm going to talk about the role of chemistry in understanding air pollution. So this picture shows India Gate in Delhi, and it shows the impact of, in this case, very poor air quality on one side and much cleaner on the other. So what's the difference between these two days? And essentially, it's the amount and the type of chemicals that are being emitted. It's their chemical reactions. And then in this case, it's very much also driven by the weather. So why is atmospheric chemistry important? So there are lots of different emissions of chemicals into the atmosphere, both from human activities, both indoors and outdoors, and then from natural sources as well. And that releases gases and particles into the air. And then these can undergo oxidation or chemical reactions in the atmosphere, and it can form thousands of different chemicals. And here I'm just concentrating on things like ozone, nitrogen dioxide, and particles that have real air quality impacts. But these chemicals have impacts across a broad range of different topics. So around health effects, they affect climate, they can cause stratospheric ozone depletion, and then they can cause ecosystem damage. So I work for both WACO and the National Centre for Atmospheric Science. And so NCAS, it's a world-leading centre for atmospheric science. And our mission really is to understand the atmosphere, how it's changing, and how it impacts life on Earth. We're a distributed NERC centre across 12 different sites, and you can see on the map that York is one of those. And air pollution is one of our main science programmes, along with climate and global change, weather, and digital atmosphere. And within our air pollution science programme, these are some of our priorities, so around emerging and poorly understood pollutants, the changing chemistry of our atmosphere, indoor air quality, and then, of course, air pollution and human health. So in WACO, there are a lot of chemists, and so we like doing lab experiments. So one of the things that we do is look at trying to understand emissions from different sources, and then we can use these to build sort of national emission inventories. So I've got two examples here. The top one is looking at emissions from domestic wood combustion, and the figure on the right shows emissions of different chemicals across different stages of the burn, so ignition, flaming, etc. And you can see that they vary. The bottom picture shows you what's called the domestic facility based in York, and it's, as you can see, a kitchen. And here we're looking at emissions during cooking. And again, you can see in the figure different chemicals coming off at different times, and this is from cooking a chicken curry. And so these are really important to be able to understand what we are emitting into the air. But once it's there, it doesn't just sit there, it undergoes chemical reactions. And so we can study these and simulate the chemistry of the atmosphere in simplistic ways in the lab. So the top picture shows the York aerosol chamber, which is pretty small, it's benchtop. And then the other picture shows you the European photoreactor, which is a really big reactor. You can see a car in the background for scale. And what we can use these for is to understand if I emit a chemical and it undergoes lots of different reactions, what are those reactions and can I follow them through? And you can see a part of a mechanism here for a compound called isoprene, which is from plants. And we can use this information to help us build models to simulate the chemistry of the atmosphere. It's also really important for us to be able to go out into the field and to measure the concentrations of different compounds. We can do this in a couple of different ways. So we can do it by shipping all our equipment out into the field. And this picture shows you a site in Delhi that we took part in recently. And what we focus on in WACO is very much going beyond the regulatory type compound monitoring and really starting to look at detailed chemistry. We can also do mobile measurements. So this is the WACO van that's instrumented inside, and it allows you to track spatially how emissions change. And the picture on the bottom is a drive around York, and the red colours show high concentrations of nitrogen oxides, which generally come from traffic, and you can see they're on the busy roads. And then the bluer colours are the more residential areas around the university. And if you want to go to an even bigger spatial scale, then we can use things like aircraft and ship-based observations. The picture shows two NERC facilities, so the RRS Discovery, which is the ship, and the FAM research aircraft that's run by NCAS. And the little figure at the bottom shows ship plumes that have been measured using the aircraft to look at how ships do they match up with the new International Maritime Organization emissions based on sulfur fuel content? And most of them did. Those observations tend to be short-term, but what's really important is also long-term observations, where we can look at really how things change over time, how policies cause changes, how global events make a difference. And so here I've got four observatories that kind of go from really urban to remote. So we've got the BT Tower Atmospheric Observatory. It's run by NCAS and the UK Centre for Ecology and Hydrology. We then have one that's slightly further out into the background. This is the Manchester Air Quality Supersite. There are actually 3 of these, so there's one in Birmingham and one in London. And they're supported by the universities and by DEFRA and by NCAS. Then we can go a little bit further out into the rural background. And so this is the Weybourne Atmospheric Observatory. And this is run by UEA and NCAS. And here we can really look at air sort of transported from London, so sort of longer range transport, but then we can look at clean air from the Arctic as well. And then finally, we've got a remote site. This is the Cabo Verde Atmospheric Observatory, and this is run by York University, NCAS, and then Tropos and Max Planck in Germany. And this is in the Atlantic. It's away from emissions, and really we can look at global trends in changes in composition. I just wanted to give one example of sort of impact of long-term observations. So this plot shows the flux of nitrogen oxide. So the good thing about the BT Tower Observatory, because it's up high, we can measure what's coming from the surface up to the observatory, so the emissions. And the pink line shows you 2017, and the red line shows you 2020 onwards. And you can see there's been a big drop in the fluxes or emissions of NOx from the surface. And that's a combination of different things, but it includes the COVID lockdowns, but it also includes lower vehicle emissions as a result of the congestion charge. Good, it works. So what we can also then do is build models. These are vital tools that allow us to look at the impacts of atmospheric chemistry reactions on a global scale. And these are built using theory and the laboratory data and the field observations. And this is a simulation of ozone formation. You can see the clock ticking quickly at the top, and ozone's formed in the day. And so you can see in this data the pulses of daily ozone being formed. But what you can also see is how that ozone's transported over much longer distances as well. We're also always striving for innovative new approaches in WACO, whether that be new instrumentation. So here we've got examples of laser-based detection systems and real-world vehicle emission testing. We're also looking at new ways that we can do experiments. So the middle top is the new interiors facility that's led by Nick Caslaw in the Environment and Geography Department. And this is to look at indoor air. And Ali showed you the picture of WACO previously, but I think it's really cool to see us embracing sustainability with our solar panels on the roof as well. And then finally, we're also looking at harnessing new digital technologies and artificial intelligence as well. And scientists from WACO and across NCAS more broadly provide expertise and guidance to a range of policymakers sort of in support of national and international policy. And there are some examples on these slides of recent reports that have involved WACO staff. And these include from the Air Quality Expert Group and also from things like the UN ozone assessment as well. And so my final slide is just to say that most of the work presented here requires us to work in partnership. And the figure here shows some of the organisations that we've worked with across policy, research and industry. And these are just a selection, and it doesn't include the many different universities that we work with, both nationally and international. And I think really what I would say is the growth of WACO over the last 10 years and really the number and variety of partners and collaborators that we have really show why atmospheric chemistry is such a vital tool to deliver clean air for all. So now I'm going to pass over to Ryan Ballard, who's the Engineering Director at JCB.
Thank you. Well, look, thank you very much, Jackie and Chris. I'm really pleased to be able to participate in tonight's discussion, and it gives me an opportunity to let people know about some of the work that we've been doing at JCB, looking at air quality and decarbonisation, and it's something that we take very, very seriously. So without further ado, I'll try and move us on. Right, okay, so the beginning of this journey really started for us at JCB thinking about CO2 and how to reduce CO2 on our machines, our road to zero. And the first thing to remember is that for us, in our sector, we don't make road going vehicles. We make off-highway equipment, and so for us, it's our off-road to zero. And I'm just going to briefly sort of explain a little bit about what our kit does and how it's used. So JCB, we manufacture a huge range of product. The sector is non-road mobile machinery, and you can see some examples there of the kinds of machinery that we manufacture. And what it's used for is infrastructure. Sometimes that's urban, and you can see some examples there. And obviously, air quality is particularly important there because of the proximity to population. But we can be working alongside roads, we can be building hospitals, houses, or obviously infrastructure in terms of power generation and putting that infrastructure in. And what that really means is that by definition, because we're fitting that infrastructure, we often don't have access to that ourselves. So a mobile decarbonisation fuel solution is essential for us. So we've developed ourselves a strategy, and this is a strategy we're following. So as I've said, our kit is used for building infrastructure. And our clean energy solution really breaks down into two different categories. For small equipment that has good access to charging infrastructure, we see electrification as the most viable solution. And obviously from a clean air perspective, that's pretty straightforward. Where it gets trickier for us is on the larger kit. Sometimes we're used in remote applications, but also used in urban applications, where the energy demand, the time required to recharge, and the access to charging infrastructure means that we need a different solution. So we've looked at many different fuels, and for us the most appealing solution is hydrogen. Obviously it's zero carbon, zero CO2 at the tailpipe, and I'll explain in a moment how we also think it gives a fantastic opportunity for improving air quality as well. So when we used hydrogen, the first step that we went through was to investigate using a fuel cell, which seems an obvious solution perhaps. And we built two prototype 20-ton machines, and you can see an example of those two machines here, situated in in our test quarry, but not, it's pretty normal application for these kinds of kit. You can see there the problems that were associated with that technology in our industry. Fuel cells have many positive virtues, but for us in our industry, they are just too expensive, complicated, and perhaps most importantly, and this was the thing that prevented us from using it in the end, simply not robust enough. They're just too fragile to use in our industry. It's a very rough, tough industry, and fuel cells simply aren't up to the job. So that made us kind of revisit internal combustion. We're already a manufacturer of diesel combustion engines, so we have some expertise and familiarity with how to do that. And as Chris mentioned earlier, over the last 2 or 3 decades, that technology has become ever more clean from a air quality perspective, and we have pretty clean diesel engines now. But really, we went back to that concept of using an engine, and because of that robustness and that familiarity, and we knew it would be suitable for our product. But perhaps the most important part is that part I've highlighted there, is what we wanted to do was emulate a fuel cell from a point of view of putting clean carbon-free fuel in, hydrogen, and we wanted the only emission from that engine to be clean steam. And that's really the what I'm going to talk to you about now. So I'm actually showing a paper here that Ali Lewis published back in 2021, which really examined sort of previous hydrogen combustion engines, which had been done maybe 20-25 years ago, and really highlighted the problem, but also within there is the opportunity associated with using hydrogen in a combustion engine. And fairly simply, if you take a hydrogen, use it in a combustion engine, particularly if you convert an existing engine, a petrol engine maybe, and burn that fuel, because of hydrogen's flame speed and temperature, it actually creates a lot of NOx, a very high amount of NOx emissions, and therefore the technology had often been dismissed because of that. Hydrogen, however, has a really fantastic and fairly unique property in that you can actually change that equivalency ratio, that air fuel ratio, and it's entirely possible to run hydrogen or run a hydrogen engine very lean. So that's a very large amount of excess oxygen in the combustion process, and that has a brilliant effect in that it reduces that combustion temperature significantly. And as we all can recognize, once we reduce the temperature that the nitrogen in the air is exposed to, the tendency to produce NOx, or the possibility to produce NOx, is grossly reduced. However, there is typically and traditionally a problem associated with that in the need to drive ever more air into the engine to achieve that lean combustion. Efficiency diminishes. So what we've worked on at JCB is to effectively take the best of both worlds. And we've done that through really revisiting the engine design from a clean sheet of paper and really optimizing every system in the engine to not only allow us to run very lean, and even leaner than those previous studies, but also to maintain the high efficiency that people have typically associated with good, efficient diesel engines. So that's been the journey we've been on for the last 4 years now. We actually started our hydrogen engine program in the middle of 2020, in the middle of COVID, in fact. And we're now at the point where we've got our engines to kind of production release. And we've been able to, pull off that trick, if you like, of getting the NOx emissions very low, but also maintaining the efficiency. So what I'm going to do now, I'm just going to take us through just a few slides to just show, how clean is the technology, how good is it? Because it's all very well to claim it, but it's great to actually seeing is believing. So we, as I say, we've built a number of engines. We've built about 150 of them now through the sort of development process, and fitted them to a number of our off-highway machines. And you can see this is an example of our backhoe loader, which most people recognize as a JCB. And as part of that, we wanted to test how clean the technology is. So we fitted this particular machine with a portable emissions measuring system that's able to measure and quantify gaseous emissions. NOx was the primary one that we were interested in. And then we subjected that to real world testing. So rather than just doing it on a test lab, which we can do, of course, but we thought on a vehicle is more fair and probably more difficult in some respects. And then we had those results independently taken and verified by those 4 different establishments that you can see there. And so there were two establishments from Europe and one from the US and another from the UK. And the results that gave us were really quite. We're really quite pleased with what that showed us. So the chart here shows how we typically quantify NOx emissions from an engine for a piece of kit like ours. Now we have to comply and do comply with the latest incumbent stage 5 emissions rules, and that has an emissions limit of 0.4 gram per kilowatt hour. So that's for every kilowatt hour of power we produce, we have to emit no more than 0.4 of a gram of NOx. And typically a good clean diesel engine would be around about the 0.25 to 0.3, giving a little bit of factor for production. So the first thing we did is we ran the engine as is, so no after treatment at all. Of course, diesel engines tend to have after treatment, and you can see already that dropped that emission from 0.4 down to 0.08, so 25% of the previous value. And then we wanted to see what would happen if we put NOx abatement after treatment. So we put an SCR system and a selective catalytic reduction system. And I'll be honest, it was straight off one of our diesel engines, so it's non-optimized for hydrogen. And that took the figure down even further, in fact, down to now 20 milligrams per kilowatt hour. So, a 95% reduction on what are already pretty clean diesel engines. Which was really interesting, fascinating to us, but we really wanted to say, well, so what? What does that mean in the environment at a sort of street pollution level, if you like? So we sort of thought, well, what does good look like? And so we had a look at the sort of various different guidelines that are out there for exposure limits for NOx. And clearly these are expressed as micrograms per meter cubed rather than grams per kilowatt hour of power produced. So we had some work to do there to kind of convert from one to the other. We focused a lot on the WHO level, the 10 micrograms, because we felt that was the most stringent level. And we then engaged with Ricardo AEA because we recognised there were a good panel of expertise to go to understand how can we convert these tailpipe NOx emissions into, what would the effect be in the environment. So we asked Ricardo to do 3 things, basically. We asked them to look at London. We picked on London just as a typical kind of urban settlement with what is, has historically had some air quality challenges there. First thing we did is ask them to baseline the London air inventory for 2019. As I said, we embarked in this work in sort of just after COVID, so we wanted to go back to a kind of normal year, or the most recent normal year. So we just wanted to look at all of the off-highway kit in 2019. Then we wanted to understand the impact of moving all of that kit to the latest stage 5 emissions limits, because today, of course, it's a mixed bag of new machinery and old machinery, and we know that new machinery is cleaner. And then the final step for us was to say what would happen if we were to turn all of that off-highway kit into a hydrogen engine, obviously in the model, to see what the effect would be. So the first step really was to break down and look at the worst case receptor that Ricardo selected was Mallet Street. That had the worst air quality characteristics, and then looked at the contribution at that site from the different emitters of NOx emissions. And you can see that road transport 25 micrograms, other, so that's boilers and other sources, and then NRMM, which is non-road mobile machinery, is down at 5.8. So already a fairly minor emitter, but measured against a scale of 10, pretty significant. And so if we kind of zoom in on that and then see what would happen if we move all of that equipment to the latest emissions limits, we can see it does bring a meaningful reduction. So there is some there's motivation for our customers really to move to the latest stage 5 diesel equipment already, and that will bring an improvement in air quality. However, it still accounts for let's say 39% of that WHO guideline. So we then asked Ricardo to rerun the model with the 20 milligrams that we'd seen on those trials that we did in our quarry, to see what effect that would have. And I guess this was when we were really pleased with the results, because you can see there that it now takes that 5.8 or even 3.9 value down to a really tiny, in fact 0.019 micrograms per meter cube. So it's a 99.7% reduction from today, and it's 500 times below that WHO limit. And I was pleased to hear Jackie talking about alternative measuring techniques, because you can see it actually falls well below the limit of the air quality measuring stations that we have available today. So clearly now the challenge is, how can we improve upon those measuring stations and drive limits down even further? So summary from a NOx point of view is really really profound for our hydrogen engine. And we started this because when we initially started to engage with government, and we were saying, well, how low do we need to get? And there were comments around zero is zero, and we can't really define zero. So for us, we feel we've defined and got to a zero impact level. I mean, it's sort of comprehend, you can always measure something, but for us a value of 0.019 against that limit of 10 really does seem to be a zero impact solution. Final couple of slides. I also wanted to talk about particulates, because as well as gaseous emissions, there's also particulate matter emitted from combustion engines, or there's certainly the possibility to do so. So you can see here the results of the difference between a stage 5 diesel engine, which again are pretty clean these days. We fit diesel particulate filters to all of our diesel engines. They do a really great job of capturing a lot of those ultrafine particles, and there's a limit that we work to of that 0.015 again grams per kilowatt hour, that specific result. But you can see there, in terms of that particulate mass, a 98% reduction for hydrogen, and that was a hydrogen engine without any filter fitted, so there's no DPF fitted to that, or HPF, or whatever you'd call it. And that makes complete sense really when you think about it, because we're no longer burning carbon. It's a hydrogen that we're combusting rather than hydrocarbon. We also verify our results and have to comply with a particle number, so we have to count that PN23 emissions limit. Our level that we have to achieve today is 1 × 10⁻¹² of those particles for every kilowatt hour that we produce. And you can see there, without any filtration applied, we're down to effectively an order of magnitude below that, 1.5 × 10⁻¹1. And then we did again run the experiment again, where we ran it with a diesel particulate filter, which is a long way from being optimized for hydrogen. And again, it's taken it down by another order of magnitude. So overall a 98% reduction. And interestingly, we're now working with some of the local universities to actually speciate that particles that we're counting, and we are starting to see some evidence that at least some of those particles that our particle counters are counting are actually water molecules rather than solid particles. So we're now working with the particle counter manufacturers and those universities to find a way to differentiate between aqueous and solid particles, to really again focus on getting that number lower and lower. So So, summary slide for me really is hydrogen combustion. We started it because we recognized we needed to do something to combat climate change, CO2. It's a really appealing solution for us because of the robustness of the technology, and it works really well in our machines. So we get that zero CO2 solution because we're no longer combusting carbon. It's hydrogen rather than a hydrocarbon. We're down to those zero impact in terms of NOx, 98% less particulates. So it's a technology that really does allow us to have that reduced CO2 and an air quality improvement as a co-benefit of the technology. So hopefully people have found that interesting as a quick window into what we're doing from an industry point of view. And at that point, I'll hand back to Tom, I think. Thank you.
Yeah, it is me indeed. Look, thank you very much indeed, all of you, for introducing your sort of different aspects of this. We're going to go into questions. I've got a few questions as well, but there are plenty of questions in the chat. And actually, the first question in the chat, I think, is possibly one of the most interesting for the people listening. So it comes from, it's anonymous, but someone says, I'm a teacher on the outskirts of Leeds. Is local air pollution something I can do anything about? Are we basically talking about something where we get the legislation, we get the technology changes, and that's it? Or as a consumer, as a person, can I plant some nice hedges or something? I mean, what do I do? Maybe let's go to Chris first.
But I think there are broadly three things people can do. The first of which is to make sure they themselves are not polluting for other people unnecessarily. And actually, there's large numbers of things you can do to achieve that. Many of which are relatively straightforward. You can also encourage people nearby not to be doing polluting activities. And an example at schools actually would be encouraging people not to idle cars near school gates, which I think is something which really is extremely harmful potentially to health over the long period. So there's a sort of simple thing that people can do. There's no reason people should carry on running their engines. They can also help people who have increased risk of health problems from air pollution, for example, children who are asthmatic, to work out ways they can try and reduce their risk. And there's a lot of information on the internet which can be passed on to people. But they can also actually help to influence government to take this as a serious issue. And if I may shamelessly plug your own newspaper, actually, Tom, the Times has done really good campaigning on this, but it needs to be seen as something which the public want, because there are many things which government can do, but they're only going to act if they feel that there is public support for this, which I think there is pretty clearly from polling and other data for outdoor air pollution at least.
Yeah. Jackie, any practical tips for things that we ourselves can do? Can chemistry help?
I mean, I think in terms of outdoor, I think Chris is pretty much covered most of it. I think the other thing to think about is what you do indoors in your homes, and to think about, if do you need to use this particular product that is really smelly, and it may smell lovely, but you're putting lots of chemicals into your home, and to think about your ventilation strategies in your house, and how you heat your home as well. So I think they're always also really important things to consider.
Yeah. I don't know if you have any thoughts either as well, Ryan, or.
Well, I think Chris made a really good point in terms of not idling. And I think, as well as encouraging people not to leave their cars, their vans, their trucks, their diggers, whatever it is, idling, most of those modern vehicles come with auto stop start, and the number of people that seem intent on turning it off is really infuriating, because as engineers, we've spent a huge amount of time perfecting that technology to turn the engine off whenever you don't need it. And I'd encourage people to let it do its thing and let it turn itself off, because Chris is right, it's a really damaging practice.
Yeah. And one question that prompted by your slides, Ryan, but I think for everyone, is you talked about sort of how low we can go. How low do we need to go? When do we say that we've one, I mean, both Chris and Jackie, you alluded to the fact that actually we've made really big progress recently and over time. And I remember chatting to an air pollution scientist about 5 years ago saying, isn't it great we're getting all of these electric vehicles? And he said, yeah, but then you got the particulates from the brake pads that are still going to be hanging around. When do we just say enough? You know, we've solved this. Jackie.
So for something like particulate matter, the evidence suggests there is no lower limit that sort of it stops being harmful, but you know, you can't completely filter everybody's air. And for some places, so the World Health Organization has, you know, these annual limits, and for some places they may never make those limits because of natural emissions. And so for me, what I think is really important is that we better understand which pollutants are particularly harmful, and say for particulate matter. So that's, you know, instead of just reducing everything, are there specific sources that we can reduce that would have the biggest health benefits?
Yeah. Yeah, and Chris, I mean, your predecessors had to deal with, you know, was it the 1953 sort of event in London where, you know, 10,000 people died over the course of a week. I mean, we've done well, haven't we?
Yeah, and compared to that, we're in a completely different place. And if you look at even 30 years ago, both space heating vehicles and industry were producing far more pollutants than they are today. But I think the straight answer to your question is we're never going to get to zero, and we shouldn't try to, because that the tail bit of it is going to be extremely difficult to get rid of, because it gets lost in the natural pollution. But we can go down a long way from where we are at the moment, and the place to start is where people live, and particularly where vulnerable people live, work, or play. So children, the elderly, I would concentrate on in particular. So if you start there and move out, I think you're making a lot of progress. And if you look at the maps in the UK, some bits of the UK really have quite low pollution, unsurprisingly, because they're in more rural areas, for example. But some of them, particularly in central urban areas, still have very high levels, and a lot of that is from things we could engineer down really a long way from where we are at the moment.
Yeah, yeah. Ryan, I'd go to you on this. Actually, we've had a lot of questions in about the technicalities of your hydrogen engines. Several are asking, you know, where are you sourcing the hydrogen from? Is this, I guess, it's, you know, is it from natural gas or is it electrolyzed water? All of these things, and then also well, do that first, and we'll move on to some more practicalities.
So, I mean, it's a question we often get asked: where does the hydrogen come from? And obviously, the perfect solution for us is electrolyzed from green electricity from renewable sources, because that's truly a net zero fuel. I think it's fair to say that the hydrogen infrastructure in the UK at the moment is somewhere behind where it needs to be. So, you know, a certain amount of the hydrogen that we've used within our test fleet has come from effectively byproduct from other chemical processes. So people who produce chlorine, for instance, at INEOS up in Runcorn, there's a byproduct there in the form of hydrogen, which we use. That being said, you know, electrolyzed solutions, we have run our recent sort of customer demonstration fleets in and around Birmingham, and there's a facility there at Tyseley Park that electrolyzes hydrogen from water with a renewable energy feed, and that for us is the perfect solution. So seeing that rolled out on a kind of more wide scale basis is exactly what we really need to make sure that we do have a true net zero solution.
And what are the compromises that you're making? Presumably you've got bigger fuel tanks, I would guess, because it's a lot less energy dense. Why would we not all be using hydrogen?
Yeah, so I mean, the big, yes, you're quite right. One of the large challenges with hydrogen is its volumetric characteristics. It takes up a lot of space. We store it on the machines pressurized, so we don't liquefy it. We did consider that, but that brings a whole new set of challenges. So we compress it, or it's stored as a compressed gas on the machines. One of the challenges we set ourselves is that for us on our machines, it's really important that our operators can perform a full day shift on one fill of gas, and then they can refill it on the shift changeover. I didn't go into it in a huge amount of detail, but our kind of kit often runs 3 shifts a day, so it might be running for 22 hours a day. and just with that short shift changeover. So as long as we can refill at that shift changeover, which we can refill in about 10 minutes, it's viable to have a tank system on the machine that will last about 8 hours or so of run time, and then a recharge basically at shift change. So it does occupy more space. It's been a big challenge for our engineers on the machine side to find places for those tanks, but they're an ingenious bunch, and we've managed to sort of squeeze them on.
Yeah, and could we? Well, one, I'll move off these, but this has really energized the audience. Why could these be adapted for cars? I mean, I know there was a period where we were thinking hydrogen or batteries, but why not downsize it, and why not upsize batteries?
Well, upsizing batteries for our machines, we did look at that, and again, I'll try and keep it brief because the context of this discussion. But to put it into context, a 20-ton excavator, that excavator that I showed as a fuel cell, that's a 20-ton excavator. Again, might be running 22 hours a day. To store enough energy on that machine for it to be able to run for 8 hours, we'd need a 1 megawatt hour battery, which is a 10-ton lithium-ion battery. And to recharge it would take somewhere between an hour to 2 hours, even at a very, very fast charge rate. And if you're in the middle of a quarry in the middle of nowhere, you're probably going to use a diesel generator to recharge it, which completely defeats the object of even bothering. So when we looked at scaling up our small electric kit, which we do have, the small kit, it doesn't scale basically for our kind of industry. So and very briefly, could it work on cars and vans? I've seen, there are companies out there that certainly have, your sort of transit vans running on hydrogen engines. There's 1 or 2 companies doing that. And for heavy goods vehicles, the 40-ton juggernauts that go them down the motorway. Again, lots and lots of US and European manufacturers looking at that as a very, very viable technology for transport. Passenger cars, we don't make passenger cars, so we'd need to talk to Ford or somebody like that maybe to get their view on that.
Yeah, fabulous. There is a sort of a follow-up to the question that we started with for Chris, I think this one. So you said that we could solve the problem, and the government often is a driving force. What sort of questions should people be asking of their MPs or councillors to get them to act on this?
Well, I think if we're talking about councillors, there's a lot that they can do locally, starting with what they buy in terms of their own fleet, because a lot of the fleet in centres of towns are owned by or heavily regulated by local councils. Road planning is a council issue. For government, I think a lot of this is about regulation, and I think Ryan would agree that a lot of what spurred that extraordinary improvement in engineering was simply the every time there was an engineering improvement, the regulators say that's fantastic, now go a bit further, and the engineers did go a bit further, but in a realistic set of steps, and using regulation in consultation with industry, so you're asking for things that are actually achievable, is what has improved things in almost all the areas I talked about: transport, industry, heavy industry, and to a lesser degree in heating. So you're getting government interested in this and saying, at any point, let's take a step forward and pass on to the next 10 years a better place. That I think is energizing for ministers if they realize they can do it and if they feel the public is behind it.
A question for Jackie. This is a question here, but I'd like to broaden it out more because I think it sort of speaks to some of your areas of expertise. So the question is about the heather burning. It's someone who lives near the moor, and the heather is burnt for half the year, and they see PM 2.5 levels rise during the burning, and they're making the point that you're not allowed to burn wet wood if it's greater than 20% moisture, but with heather it's 38% moisture, and they want to know what impact this might have on health. But presumably when you look globally, there are all sorts of other sources of pollution like this that can have quite large localized effects, or do they not? Do they actually disperse quite quickly if you're burning things outside like that?
So in the case of the heather burning, it's not really my area, but I know that you have to have licenses and so on to be able to do that. But I can imagine that you do get quite a lot of particulate matter emitted from those practices. And I think if you look in other countries, so places like India, some of their bigger pollution events are from stubble burning. So at the end of the agricultural season, they burn stubble. And what we're also going to see is, we're already starting to see it with climate change and with the warming world, that wildfire occurrence and intensity is going to increase. We've just seen that in Los Angeles the other week. And actually, these small localized events can have big impacts on a much wider area. So, and especially for things like wildfires that do end up going into residential areas, you're burning plastics and metals and all sorts of materials that can be really toxic. So I think whenever you burn something, or whenever something is burning, the emissions from those are really not great for your health.
Talking of burning plastics and things, there's a question about smoking and cigarettes. So cigarette smoking's gone down, so we don't have that source of indoor air pollution. Do any of the panelists, Jackie, Chris, or Ryan, do you have any views on or any knowledge about what vaping might do? Not to the individual, but I think it's probably outside of your remit, Ryan, certainly. But has anyone even looked at this as a new source of indoor air pollution?
So if I come in, I've done quite a bit on smoking indoors, and actually how it sticks to surfaces and it can cause problems long after somebody's been smoking. There's quite a lot of work going on looking at emissions from vaping. It's a very different mixture of chemicals, and so I think there's still quite a lot that needs to be done on those harmful effects from the sort of second-hand vape, and so on. But maybe Chris can say more on this one.
Yeah, I mean, I think we're very confident that vaping is less harmful as a second-hand thing than second-hand cigarette smoke. But that's simply because second-hand cigarette smoke is so dangerous that being safer than that is setting the bar unbelievably low. I think equally, most people assume that certainly for people who vape themselves, who are taking a very high concentration of things into their lungs, and very possibly for many vapes down a wind of someone, you are certainly increasing your risk compared to not having it in the first place. And I think what we've learned from air pollution is that things you can't either smell or see can still do significant damage if they're absorbed through the lungs. So there's a lot of stuff which if you swallowed it, your body would deal with it absolutely fine. But if you absorb it through the lungs, which actually is a very kind of small barrier between the outdoors and your bloodstream, the damage can be quite significant. And I talked about the effects of air pollution on cardiovascular disease, stroke, and heart attacks in particular. That's probably due to inflammation indirectly caused by things absorbed through the lungs. So, I mean, my advice is very simple, which is if you smoke, then vaping is going to be safer, and you can, in a sense, think of it as a form of air pollution if you wish. But if you don't smoke, just don't vape, because we don't know what the long-term effects will be because we haven't had them for long enough, and it took us several decades to work out exactly what cigarette smoke did. So I think the very strong advice would be don't do it if you're not a smoker already.
Yeah. There's a couple of questions which might be best directed to Chris as well, but there's a couple of questions on ventilation. This became a big thing in the pandemic, but it's presumably so you get the double win of bugs and air pollution. What sort of strategies are there that could improve indoor air quality in hospitals, for instance, and practically in not in new houses, but in the houses we have already? What are the things that we can do? We'll start with Chris, and then it looks like Jackie's got something to say on this.
Well, I think fundamentally what you have to do is reduce emissions and increase ventilation. Those are the two things you can do to reduce indoor air pollution. It's more complicated than that, obviously. Now, in the case of reducing emissions, some of these things are relatively obvious things, starting actually at the extreme end with smoking, but going through to, for example, opening the window if you're doing smoky kind of cooking. Is a sensible thing to do, and that's where you've got an emission, but you can reduce the local emission by just diluting it out. I think people just do that out of common sense, to be honest. The difficulty comes with ventilation when you've actually got a trade-off, and this is, otherwise we just have all the windows open the whole time. But actually, for example, at this time of year, most people want to stay warm, and the nation and all of people who've really thought about it want to reduce carbon emissions. So we don't want people to be producing heat, which essentially goes straight out the window. So the engineering challenge is simultaneously to maintain a good level of ventilation and to reduce the amount of heat that's lost via that mechanism. And there are ways that can be done, heat exchangers and a variety of other things, particularly in big public buildings like hospitals or government buildings or whatever. So, I think we should see this as an engineering challenge that we've now got to meet. And the problem we have at the moment is the engineers who look at ventilation and the engineers who look at heating tend to be thinking in separate sort of stovepipes. And I think we need to bring those two together.
Jackie, do you have any thoughts on this?
Yeah, so thinking about people's houses, so we've just done some measurements in 300 households in Bradford, looking at the particulate matter, and one of the main sources is cooking. And actually turning on your ventilation, so your extractor hood, is a really effective way of reducing your exposure. So during cooking and then after the cooking period as well. And if that can be supplemented with opening windows, if that's possible. Also, the other trade-off that Chris was talking about is also if the outdoor pollution is really high, then bringing that inside is not really what you want either. But using things like extractor fans, they're really effective at removing some of those sort of high emissions during cooking.
Yeah. Ryan, I don't know if you have thoughts on this, but we have lots more questions about JCBs. One of the questions is, and do feel free to comment on this as well, but one of the questions occurred to me as well. Can you talk through why combusting hydrogen produces NOx and particle emissions? What's going on there? Because we can all do the GCSE chemistry and just like, well, you've got your water and that's fine.
I mean, the first mechanism really is oxides of nitrogen. So obviously the air that the engine is bringing in, and we're combusting with the hydrogen. We're combusting the oxygen and the hydrogen together to get H2O. But one of the tendencies of hydrogen, if you run it at sort of where we use all of the available oxygen, so at its stoichiometric ratio, if you like, so complete combustion, it burns very hot. Hydrogen has a very high flame temperature. So that has the negative effect of heating the nitrogen in the air, the 80% of the air is nitrogen approximately, to those very high temperatures. And obviously then that gives it the ability to oxidize, and it increases that ability to oxidize. However, as I said in my presentation, one of the virtues of hydrogen is that you can still get it to combust at it's got a very, very wide range of flammability. So, simply put, you can still get good, effective, stable combustion of hydrogen without using all of the oxygen present. And that's quite different to a hydrocarbon fuel like petrol, for instance, where if you try and run a petrol engine with too much excess air, it'll sort of cough and splutter, and as engineers we call it lean misfire, and you get poor combustion. Hydrogen's different to that. You can run it very, very lean. As you run it very lean, it reduces the flame temperature. Because the flame temperature is reduced, the nitrogen doesn't get as hot, and therefore it's not able to oxidize, and you don't create the oxides of nitrogen, or far less of them in the combustion chamber. And that was the approach we used, was to deal with the NOx problem, if you want to think of it like that, at source in the combustion chamber. So that's why, the NOx it is possible to reduce the NOx, as we've shown with that internal combustion process. In terms of the mechanism for creating particulates, it is almost completely eradicated, almost, in the form that obviously we're not burning carbon, so we're not creating little bits of soot, carbon-based particles. That being said, because it's an engine, there is still a very small amount of lubrication oil inside the engine, and a tiny amount of that does get consumed during combustion. So, I mean, we love a challenge, engineers. So our next challenge, and we're genuinely trying to find out, can we derive a carbon-free lubrication oil so that then we can get rid of that tiny influence as well. And I think Jackie, or maybe Chris, both said it, in terms of how low can you go for particulates, even to the point where, maybe there's tiny wear particles of, different bits of the engine rubbing against one another. But, we're always looking to find ways to different coatings, different lubrication techniques to try to get that lower and lower and lower.
So what is a carbon-free oil? I mean,
well, quite, and I was literally only discussing this with our in-house chemist yesterday, and she's not quite sure how we're going to do it just yet, but she's certainly up for the challenge. So yeah, we're engaged with various lubrication specialists around the world to try and find out how to do it.
Could I just add to Ryan's thing, because I think it's often misunderstood that this is also a problem for if we were to use hydrogen for cooking and space heating. So this issue is not just to do with engines; it's actually to do with the burning of hydrogen at very high temperatures.
Yeah. Well, two more questions on cooking with gas. So Dave Merritt is asking whether the cooking process or the cooking with gas is one of the big issues domestically. Is it the thing you're heating it with, or the thing that's being heated? And then Mark has said, and I know Chris, for very good reasons, you're sort of slightly wary of slightly political things. This slightly strays into it, particularly with energy prices at the moment. But at the moment, Mark Taylor's making the point. At the moment, we don't really have taxes on gas. We do have taxes on electricity. And that's one of the reasons why gas is so much less expensive than electricity as a fuel for cooking and heating. Is that something that we need to look at? So Jackie, on I guess certainly on the first, you presumably have thoughts.
Yeah, so it's both. So if you have a gas stove, then you will definitely be getting particle emissions from your gas stove. And then what we've seen is a very big variety of emissions based on how you cook and what you're cooking. So if you're boiling, you tend to get quite low emissions. If you're frying, you get really sort of higher emissions, particularly a lot of the fat turns into particles. And then you also get lots of gas emissions. And so what we've been looking at is, if you cook and you put lots of herbs in, it smells lovely, but that means you're releasing lots of volatile compounds into the air. Now, whether they are harmful or not is a question that's still up in the air. But I think if you can avoid a gas cooker, that's a really good option. And there's been some recent work from Birmingham using air fryers and showing that they can have quite low emissions as well compared to like open pan frying. So there are quite a few options that you can try and reduce your emissions during cooking. And I'll pass the second question over to Chris.
Yeah, I'm not going to be particularly political, and if I started trying to make tax policy, I'd get a call from the Treasury at the end of this particular session. But I think the general point, which is one of the most effective ways historically we have always used, one of the most effective tools to change air pollution has been taxation, and you can use it in positive ways. You can use it in negative ways. Some of the tax changes that really underpinned, for example, the move towards diesel light vehicles in the early part of this century actually were good for carbon, were bad for air pollution. It was an example actually of a policy which went in two opposite directions. But the move towards electrification of the light vehicle fleet, so private cars and small vans, that's around the world being driven by changes in tax policy where they are benefited in terms of taxation. So certainly taxation can be a way in which you can encourage change, and that often is simply to do with putting more tax on the thing which does the thing you don't want it to do, and less tax on the thing that you do, and therefore leading to overall changes.
Yeah, yeah. And I mean, I used to live on the South Circular, so I'm completely aware of what air pollution is and what it does. But at what point, again, do we sort of say, I like the smell of burning herbs or sort of, cooking herbs? Humans have done so since humans have existed. This sounds heretical. I really like the smell of wood smoke as well. Are these things we really need to be worrying about just yet?
I think there are two answers to that. I mean, the first one is, if you're imposing it on other people who have no choice, then I think there's a bit of a concern. And that's really, for example, why the Clean Air Acts happened in London in response to the appalling smogs of the 1950s. And that led to lots of people not dying who otherwise would have died because it was affecting other people. If people wish to do something and they enjoy it and they're well aware of what the risks are and it's not addictive, that's a very important difference from smoking, to be clear, before someone tries to drive some kind of thing. That's where I think most people feel a little bit queasy telling someone what to do, provided they're aware of the effects. But for example, were someone to really love their open fire, but they had a child who had really bad asthma, I would advise them not to do it. Not because I want to be a spoilsport on their fire, but because it's going to cause harm to their child. So I think it's really just getting the balance right between these. But I think the thing about outdoor air pollution is you are going to affect other people, and that's really the reason why I think most people think it is reasonable for the state to take a view on that.
Yeah. Should we? There is one that's just come in, and constantly coming to the end of time. But Caroline McDermott has asked the wood burning stove question, the sort of the middle class thing. Is there evidence of a negative impact on health? Should all middle class people be stopping using these? And also, could chemistry or engineering come to our rescue and find a way of sort of making better stoves that'll filter it all out?
Yeah, let me walk into the minefield and be written angry letters by all my friends. But there is no doubt that solid fuels of any sort produce a lot more particulates than any of the other forms of heating. Oil is better and gas is a lot better and electricity is zero. So if you're just trying to get the room heated, just be aware you're going to lead to pollution, probably indoors and outdoors. That said, if someone's living in a remote rural area and they're using a wood burner and there's no one for miles around, they know that there's probably some additional risk, and I take a pretty relaxed view about that. I would take a slightly less relaxed view if huge numbers of these are happening, around an old people's home in a central London area, for example. I think there's a balance of what is reasonable. But the other thing you say on engineering, modern stoves, the eco-designed stoves, produce a lot less air pollutants than the stoves that were being sold typically 20 or even 15, 10 years ago. So modern stoves are a lot better. So if you wish to have a stove, have a modern stove. And if you wish to have a stove, use very dry wood, because it makes a big difference about how much pollutant comes out. Is it very dry wood or is it damp wood? And then finally, don't use it around people who are very vulnerable if you can avoid it, and kind of minimize it to what gives you pleasure, but don't keep the thing running the whole time if you're on a relatively built up area, because you will be having an effect on other people. It's about being a good neighbor, is my view, to be honest, rather than anything else. But I would go back. There are some areas where the density of population is so great, and that's the reason why clean air zones were invented, and they did make an enormous difference. So it's really just getting a balance of answer, I think.
Jackie and Ryan, do either of you want to sort of put your foot into this debate?
I think from my point of view, sort of listening to Chris's points, I think they're all pretty sensible and valid points. And in terms of kind of the engineering, it's it's absolutely true, isn't it? A more modern stove, significantly cleaner than an old one. It really goes to show, it's all about managing those combustion temperatures. Is there more that can be done? I don't know, perhaps, but ultimately burning wood, it is combusting pure carbon, and therefore, there's a CO2 perspective there. I know there's an argument it's net zero because it's been absorbed from the atmosphere, but it's actually probably far better to leave it locked away, that carbon, for as long as possible, and maybe use an alternative fuel source.
Jackie, final word to you.
And I don't think I have anything much to add. I think Chris was really clear on that. I think if you live in a built-up area and you have an alternative means to heat your house, then really you have to think about the impact on your community and the vulnerable people, and if you have them in your life. I think if you live in a rural area and there's no other fuel source, then being as efficient as you can with dry wood, and you operating your stove properly and having it cleaned, these are all ways to minimize emissions.
Look, well, thank you very much. Thank you so much, everyone, for your questions as well. I'm sorry if we didn't get to yours. I'm now going to, well, look, thank you to the panelists. Thanks for taking time on a Friday evening to do this. I'm going to hand over to Professor Sarah Thompson, Interim Pro-Vice Chancellor of Research, to end the session and say goodbye.
Thank you, Tom, and thank you, everybody. So what an engaging and stimulating discussion that we've had, and also a huge amount of practical advice. So thank you to all our panelists for sharing your different expertise and creativity in approaching the Clean Air Challenge. And not least to you, Tom, for so expertly chairing the session and choreographing all our questions. And in fact, a good discussion most definitely depends on the quality of the questions. So thank you too to the audience for a wonderful range of questions touching on so many different aspects of clean air. But this evening's been perhaps more than just the discussion. It's also been a celebration and a demonstration of the important work that WACL has been doing over the first 10 years of its existence, and how the next decade and beyond is critical to improving our air quality and public health. We've also witnessed a few other things about the importance of designing research and communicating the science that's carried out in WACL to the people who can actually use it. And it also shows why we need to work with non-academic partners and users of scientific research from global companies such as JCB and government departments and schools to ensure that our research-related skills and expertise benefit the society and our economy. We hear the National Environment Research Council say that most environmental science is relevant to policy, whether in the short, long or very long term. And that's absolutely true of the work that we've been discussing this evening. So just perhaps a couple of other things about York. We're really proud of the work that we do in York that connects environmental policy to innovation in industry. And not just the examples that we've heard tonight about clean net zero combustion, but also chemical manufacturers, consumer product industries, agriculture, energy generators. All of those have huge impact. This kind of research is perhaps also an excellent demonstration of our commitment to be a university for the public good, because it illustrates how our university community, the curiosity, power of collaboration. Let's have more occasions where we have atmospheric chemists, medical professionals and engineers in the same room, please. It shows how we explore the unknown, we push the boundaries of knowledge, but we actively pursue, practical solutions to local and global, and as Chris said, shared challenges. And with our partners, we can tackle those most challenging questions and create something better for all of us. And that's what we mean when we say we're a university for the public good. So thank you all for joining tonight to celebrate these first 10 years of the Wolfson Atmospheric Chemistry Laboratories with us. Thank you again to Ali for his introduction, to Chris, Jackie, Ryan and Tom for such a stimulating and insightful conversation, and enjoy the rest of your evening.